Hi, in this video, let us engage in an informal and intuitive discussion on the concept of limits. Limits are a central concept in calculus. So today we will not give any precise definition, but using examples, we'll try to develop an intuitive idea for what it means to use this word limit. So let's look at the first example I have here on the board. I have a sequence of numbers. For now, it's enough to think of a sequence as a list of some numbers. And in this example, we'll try to see what it means to say limit of a sequence. So let's take a closer look at the numbers that I have listed out here. 0.9 or 9/10. That is a number, so it's a point on the number line, and you will see it's pretty close to 1. It's 0.1 units away from 1. And now let's look at 0.99. That's only 0.01 or 1/100th unit away from 1. So we can see from our understanding of finite decimals that the second element is even closer to 1 than is 0.9. And you can argue again 0.999, if you were to plot it, that would be even closer to 1. So you're developing an intuitive understanding that as you go down this list and plot the points on the number line, each one down the list is going to get closer to 1 and closer to 1 and closer to 1 and so on. Notice that 1 itself is not in the list or in this sequence. Another way of saying it is any number you pick from the list, if you were to plot it, you would never put it on the same dot that represents 1. It will be very close to 1, but it will not be 1 itself. So there's no element in the sequence that's exactly 1. And yet, as we begin to plot the points on the number line, each one down the list is getting closer and closer and closer to 1. So here are the observations. The number 1 is not an element of the sequence, and we are somehow developing an intuitive and informal idea to use this kind of vocabulary. The limit of the sequence is 1. Another way of saying it is, if we were to plot these numbers, those numbers are getting closer and closer and closer to 1. Now, if you were to make this very precise in an advanced calculus class, then you would have to use precise definition to give a meaning for what closer to 1 means. Here's our second example, where we have a sequence of regular polygons. Here the elements in the sequence are not numbers, they are figures. Let's get into the details. I have a circle here. P3 refers to an equilateral triangle that I fit in like this. The vertices of the triangle are on the circle and the 3 side lengths are equal. So we can think of P3 as a polygon with 3 sides and the vertices lie on a circle. P4 is a polygon, regular polygon with 4 sides, that is simply a square, so that the vertices lie on the circle. Now you get the idea. P5 would be a pentagon, which I have not drawn. It would be a regular pentagon with its 5 vertices sitting on the circle, and all the 5 lengths are equal. So visualize the rest of the figures that I have not drawn here and think about what we notice visually about those figures. Notice first, the circle is not an element of this sequence of regular polygons. Each of this polygon is made up of straight line segments, and as you can see from our intuitive idea of the circle is not made up of straight line segments. And yet, even without any precise definition, we all seem to have a way to visualize the sentence as n increases. Remember, n refers to the number of sides of my regular polygon, or number of vertices of the polygon that sit on the circle. As that number increases, the polygon figure, PN, whatever figure you're drawing, it approaches the actual circle itself. As you can see here, we have a triangle. Then I drew my square. So if you drew your pentagon and then the hexagon, then think about, by the time you draw your regular polygon with, say, 1000 vertices, all the vertices lie on the circle and all the side lengths are equal, and that regular polygon with 1000 sides, you get the feeling it looks almost like your circle. It is not your circle, but you feel it looks like the circle. So this is all developing an intuitive idea of limits. The ancient Greeks did have an understanding of this intuitive idea, even though the word limit in calculus did not exist in their times. Keep this idea in mind. Here's my third and final example for our informal and intuitive discussion of limit. So in this context, here's how we use the word limit. I have here the graph of a function, that is this black curve, if you can see it, and I picked a point P on the curve. I picked another point Q on the curve, which is the graph of y equals f of x, and I connected P and Q by a straight line, and I'm calling that the secant line. Now visualize that this second point that I picked, Q, visualize it sliding towards P along the black curve. As you do that, also think about the secant line that connects P to that new point wherever you slide Q to. That's also a secant line. Let's call it a secant line. So as Q slides down, think of what happens to the secant line that connects P to the point Q as Q slides. So you'll see here I've drawn two positions. If Q is that point, then that's the secant line. If Q slides to this point, then that's the secant line. So in your head, visualize as Q slides towards P, what happens to the sequence of those secant lines. You will realize that the secant lines slowly approach this red line, which is called the tangent line. So in other words, here's an informal way to think about the tangent line. It is in fact the limiting position of the sequence of these secant lines that I just described. So to think about the tangent line at P, think of another point, a point distinct from P on the graph. Connect those 2 points, call that the secant line. Now as you slide Q toward P, think about what's happening to the sequence of those secant lines. If they do approach to a limiting position, in this case they do, then that limiting position is what we're calling the tangent line. And this completes our informal and intuitive discussion of this word limit. The concept of limit is very important in calculus. It is this idea forms the foundation of calculus. Thank you.